Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a final video for differential calculus students when it comes to learning about secant lines, average rates of change, tangent lines, and instantaneous rates of change. There's a little subtopic in there called average and instantaneous velocities. And this is a single example video because that's all you really need for this topic. Average and instantaneous velocities are intimately related to average rates of change and instantaneous rates of change. Why? Well, think about a velocity. I'm going to scroll down here. I just want to showcase something. Suppose you had a graph that represented how many miles away from an initial point you were at any given time. And time is given in terms of hours here. And again, m is the number of miles that you've driven. So for example, at time 0, you've driven 0 miles. But let's pretend at time 1, let's pretend that that's what this is, hour 1, you are, let's pretend, 50 miles away from your initial origin. And at hour 2, you are, oh, I don't know, that looks like maybe 55 miles away from your original origin. And maybe way over here at hour, well, if that's 1, 2, maybe this is hour 6 or something like that, you might be approximately, let's say 90 miles away from your initial state of origin. If you want to compute the slope or the average rate of change between any two of these points, that would end up being, well, let's find out what it is actually. Let's plot these points and then connect them. So that average rate of change, the average rate of change, remember, is just a slope of that secant line connecting those 2 points. But also remember, slope is rise over run. So in this case, you've risen 35 units, and the units for the vertical axis are miles. So your rise is 35 miles. Your run is in terms of hours, and this distance here is a distance of 4. So you've gone 35 miles in 4 hours. And so that average rate of change could be interpreted, remember, slope is rise over run, as 35 miles per 4 hours, or in other words, it could be interpreted as a certain speed of velocity, 35 miles per 4 hours, or if you did the math, that's about 8.75 miles per hour. It's exactly 8.75 miles per hour. Not very fast, but nobody really cares about that. What's important here is that the interpretation of the units there, or what the units become, tells us that this is a velocity. So the average rate of change in a physical situation when you're doing distance over time is actually just an average velocity. And if you want to find the instantaneous rate of change at, let's say, this moment right here, that would be the instantaneous velocity. So that's not even a difference. That's the only thing you really truthfully need to remember when you're dealing with distances and times, is that the average rate of change ends up being the average velocity, and the instantaneous rate of change ends up being the instantaneous velocity. So let's go ahead and see how this works. The table below shows the position of a motorcyclist after accelerating from rest. So at 0 seconds, that motorcycle rider is 0 feet ahead. At 1 second, they're 4.9 feet, 2 seconds are 20.6 feet, and so on and so forth down the line. Find the average velocity for each of the following periods. So the average velocities between time, or the average velocity, sorry, between time 2 and time 4. Well, if the average velocity is just a fancy way of saying average rate of change, which is another way of saying slope, then really they're just saying what is the slope between time 2 and time 4 on this curve. You don't see a curve, but there is a curve behind the scenes. Remember, it's the difference in the y values over the difference in the x values. Well, the y values here, let's see, for time 2, well, let's do with 4. Time 4, the y value is 79.2. So that's the distance at time 4 seconds. And then at time 2 seconds, it's 20.6 is what the output is. And there we would have, once we actually do the computation, the average velocity, which in this case is 29.3. And let's go ahead and put some units on that. Rise over run, rise is in feet, run is in seconds, so that'll be feet per second. That is the average velocity between the second and fourth seconds. Now they're asking, what about the average velocity between the third and the fourth seconds? Well, let's go ahead and find out. As we did before, it's just a difference in their outputs divided by the difference in their inputs, the corresponding inputs, that is. It's actually not a ton of work there. The only thing you really have to do now is just grab a calculator and compute that out. It's 32.7. And don't forget, it is in feet per second. Now I want to draw your attention to something here. The average velocity or average speed in these time periods does change drastically. Between 2 and 4 seconds, the average speed was 29.3, but then when you tighten up the time period to go only from 3 to 4 seconds, it's a slightly faster speed. Let's go ahead and find out the average speeds between 4 and 5 and 4 and 6. Notice how I have that set up. It's just the input of 4, and on the top it's the output of 79.2, and on the bottom again it's the input of 5 and 6, and on the top I'll have the outputs at second 5, which is 124.8, and the output at time 6, which is 176.7. Again, I recommend in these cases you can just quickly grab a calculator. It's not that big of a deal to have a calculator on hand every once in a while. And doing this one, we see that we're actually speeding up 45.6 feet per second. Finally, the last one gives us 48.75 feet per second. Now, all of this is computational, and most students can quickly compute stuff like this. What throws off a lot of students is when you say, well, use the graph of your function as a function of time to estimate the instantaneous velocity when t is equal to 3. That usually throws people off. So let's go ahead and go to Desmos and talk about that. So over in Desmos, we go ahead and go to the graphing calculator area because that's going to be helpful. We're going to build a table of values to visualize this data. And what I'm going to do is copy and paste in a table. So off to the right hand side of the screen, which you cannot see, I have the data in a table in Excel, and I'll just come back here and I'll click, or I'll do Control V to paste it, and it immediately pastes in the data, and Desmos will automatically zoom to fit your data. That's actually really nice. Now we want to know the instantaneous rate of change at time 3. With discrete data like this, and let me be very clear what I mean by discrete data. Continuous data is data that is built from a continuous curve, a nice clean curve. But in this case, we don't have a nice clean curve that's been handed to us. We've been given data points. And so when you've been given data points with space in between, that's called discrete data. And when handed this discrete data, it's incredibly difficult, if not impossible, to find instantaneous velocities or instantaneous rates of change because you don't have a curve to bring 2 points close together. The best you can hope to do is possibly just take averages of slopes to find out what the possible or approximate instantaneous rate of change is. Since our goal is to find the instantaneous rate of change or the instantaneous velocity, or basically the slope of the tangent line at time 3, it would be wise to build an equation of a line at t equals 3 and y when t is 3. T being the value of x here, by the way. So to do that, I'm just going to write in y minus y sub 1, but the output at time 3 is 46.5, is equal to some slope, which we don't know, times x minus x sub 1, which again, we're dealing with the point 3, comma, 46.5. And then you could add a slider here and just fiddle around with different slopes that might represent this. You can easily see that the value of the slope, the instantaneous slope there, likely is much greater than 10. So let's go ahead and adjust this and say that this goes from 10 to 30, and we'll step at step sizes of 0.1, for example, just to showcase this. And as you do that, man, even 30 might not be a good boundary. Let's go from 20 to 40. And now you'll see that the slope of the tangent line may be right around there, because if you connect these dots along this curve, it looks as though that might be the slope of the tangent line at that very moment. You have to do a lot of visualization here. So in my head, I think it might be around a 29. And as you can see, I actually included some equations in here, and these equations represent the work we've done just a moment ago when we found those slopes of the lines going through, for example, this first one. Let me turn off this line right here. This first line represents the secant line that goes through time 2 and time 4, the points at x equals 2 and x equals 4 there. And we found the slope of that line to be 29.3. And then the next one represents if we used the points 3 and 4, and that would give us a slope of 32.7. And the next one would be the slope of the line connecting points 4 and 5, and finally the line connecting points 4 and 6. Altogether, it can look like a bit of a mess if you turn all these on at once, but it gives you a tactic actually for finding the slope of the tangent line at time 3. You can take some averages. Really, the 4 and 6 situations aren't going to really help, but the line, the blue line and the green line there, give me secant lines between time 2 and 4 and times 3 and 4. And that allows me to approximate slightly, maybe by averaging those two slopes there, I can get an approximation for the slope of the tangent line at time 3. So that's a good recommendation, maybe just averaging those two slopes. So I'll just pretend for right now that the slope of the tangent line, or in other words, the instantaneous velocity at time 3, is just the average of the velocities, of the average velocities between times 2 and 4 and times 3 and 4. And you can actually get a pretty decent approximation by taking the average of the slopes between times 2 and 3 and 3 and 4. Note in this case, it's saying the average is 31. So if I turn back on our tangent line, turn off these silly ones, and I change that slope to a 31, it's saying that the slope, the instantaneous velocity, or the slope of the tangent line at time 3 should be about 31. And that might be actually correct. I would say it's probably less than that. Again, maybe around 29. But another way, like I said, to approximate this is to use the average of the average velocities between times 2 and 3, and then between times 3 and 4. Since we already know the average velocity between times 3 and 4 is going to be 32, turn that off there so you can see it. Let's just quickly compute the average velocity between times 2 and 3. You see on the table up here, we have all the information we need. So let's go ahead and do that. I typed down here, m sub 2 comma 3 just means to me that it's the slope connecting the lines at x equals 2, or the points at x equals 2 and x equals 3. So let's go ahead and compute that. It's a difference in their outputs. So that'd be 46.5 minus 20.6, and then divided by the difference between 3 and 2, which is 1. And so when you do that, oh, I see that Desmos does not like my subscript with commas. So let's just call it m sub 2 for now. we get that slope is 25.9, yeah. And remember, the slope between 3 and 4, I'll call that m sub 4 just to make my life a little bit easier, was 32.7. And so if you want to find the average of those and call that the slope at time 3, you can say, well, that's just the slope at time 2, let's go ahead and do that, plus the slope at time 4. And you can see that using that averaging method, it tells us that the slope of our tangent line at time 3 should approximately be 29.3. That is the instantaneous velocity, should be 29.3. Let's go ahead and see if that's actually true or looks to be true. So I'm going to go down to 29.3, and I have to admit, I think this looks pretty good. All right, so that's what I would say is the best way, or one of the ways, I should say, of approximating the instantaneous velocity or the instantaneous rate of change given discrete data. Just find the average rates of change for neighboring points and then average those averages. This rounds out the lecture video series for secants and tangent lines as an introduction to limits. In the next set of videos, you start going into what an actual limit is. Not the precise definition, but kind of a general overview of what is a limit. I'll see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.